good to see you all here. How many have heard of propensity score matching? Used it? Okay, great. My research interests are primarily focused on this problem of teacher accountability, particularly as tied to high stakes tests. And that passion I've kind of had, that focus I've had, has led me to become more focused on some methodological interests as well. And so this project that I'm going to show you a little bit today is a simulation-based project that I've been working on, and I have some preliminary results based on some concerns I had with the propensity score matching approach that I was using. So just as a little bit of background here, this way. The school and teacher accountability issue. We have high-stakes decisions being made about teachers by trying to link student test scores to the teacher. There are a couple of different models that are being used statistically. One is value-added modeling, which is basically linear regression. And then we have student growth percentiles, which is kind of a newer thing a lot of people are using, including in the state of Utah. That's an entirely different approach. There's some evidence out there that both of these approaches produce bias estimates, but there's not a lot of consensus about how much bias, when is there bias, what's the problems resulting from that bias, are we making poor decisions about teachers, how often, and so forth. And then what do we do about that bias? Is there any other way that we can ameliorate that to some degree at least? And so in order to explain that, I'm going to give a little bit of background. First of all, value-added models. Basically, they're linear regression models. In the simplest case, it might look like this. This is just a matrix with a whole bunch of covariates. What have you got? It might be prior test scores. There would be prior test scores in a value-added model. But it might include other stuff, other things we've measured on the teachers that we think might contribute to test score gains. And then right here is just basically the teacher effect. And that can be random or fixed depending on what kind of model you're using. I won't go into that a lot right now. But what I wanted to point out is that one of the big assumptions in the value-added or any regression model is linearity. And I'm going to show you a little bit about what that means. It's something to help me understand it. If you imagine that these little green dots are a response or to an outcome, say like an end-of-year test score, for students who didn't have some treatment, they're a control group, okay? And then the dark green are ones who did have a treatment. And just the lines are to help you to see the height because it's hard to see things in 3D. So essentially we're trying to figure out in some way or other what's the difference between the outcome of those with the light green circles and the dark green circles, the controlled versus treated units. And this could apply to any situation in which where you have a treatment control group, not just in the teacher scenario, we treat each teacher as a treatment, but I'm going to back away from that and go a little more general for a little bit here. So that's essentially what's happening. And somehow we're trying to find out what's the average difference between those two groups. Well, in an ideal world, of course, you'd have every person would be treated and untreated, and then you could look at those differences. That doesn't happen. And so what we do is we do the best we can some other way. At best, we might hope that here this is just, we're assuming two covariates, okay? This axis is a covariate, this is another covariate, the height is the outcome. And you have to imagine this expanded to how many dimensions, how many covariates you have. If you have 20 covariates, you'd have 21-dimensional space to represent this. So we're just going to think about two covariates for today. And we think about that, we have to, at best, we can assume that these light green units and dark green units will be distributed over the same space with respect to covariate A and B. I mean, the light greens are not clumped here and the dark greens up here. That's the best we often get in kind of an observational study. So what ends up happening with a linear model, what we're trying to do is we're trying to force fit, if there's two covariates, two planes through the data, and we're forcing those two planes to be parallel, unless we include some other interaction terms and things in the model. But for the most part, that's what we're trying to force to happen. And the distance between those two planes we call our treatment effect. That's the difference between the two groups. So if you look at this visually, you can imagine some problems here. One possibility is planes don't fit well, right? Okay, maybe they should be curved. That's a possibility. Another possibility is that the planes shouldn't be parallel. If the planes aren't parallel, what it really means is this treatment effect gets bigger as one of the covariates get bigger or small. Okay, that's another, would be a violation of the linearity assumption. And both of those, if they exist, anything like that exists, basically we're trying to fit two parallel planes through something where that just doesn't work. So our estimates are going to be biased. Okay. Another problem you could imagine happening is suppose that you had all the light green units clumped, and down here and the dark green up here, we're doing a lot of extrapolating, which is we're assuming that whatever happens up here I can extend way down for this plane. Whatever happens down here I can extend up. Or if there's missing gaps in the middle, I'm interpolating in between. I'm assuming that what happens at the extremes happens in between. So we're doing this big simplification of reality in order to make a linear model fit. And with just 2 dimensions, you can visualize it. Again, 3 dimensions, it gets a little bit rougher to figure out. So from that, I just wanted to point out what some of the problems could be. And if any of those problems exist, we can end up with bias. In other words, our estimate as to that treatment effect could be way off. Okay. So an alternative. One alternative is a matching approach. And there's a whole bunch of matching approaches, a whole family of ways that you can match. Essentially what we're trying to do is we take our treated units and our control units and we find the ones that match up the best, that are closest together in some way. When we do that, propensity score method is one method, and so I'm going to talk a little bit more about today. You end up approximating random assignment by matching a treated subject to the control subject that was just as likely to have ended up in the treatment group. We're going to come back to how we do that in a little bit. Okay. If I look at this picture again, now I have the light green units and the dark green units again. Instead of trying to fit these planes to them, we're going to do something really different, which is I'm going to try to find, for each dark green unit, a light green unit is the closest to it in the covariate plane. So if you just think of this floor here, trying to find those that are closest. And again, if it was more than 2 dimensions, it would be analogous, just harder to visualize. Okay, so I'm trying some way. Now, how you decide closest, or what distance, how you measure that distance, there's a lot of approaches to that. If you remember from high school algebra, just Pythagorean theorem, where the distance a squared is b squared equals c squared, use that to get distance. That's a Euclidean distance. It's just how close those are together. There's a Mahalanobis distance, which is similar, except for we adjust for the correlation between the variables on their scale. A little bit different. Propensity scores take an entirely different approach, and I'll show you what that is in just a minute. And the key is I'm trying to find the distance between the closest pairs. If I do that, then what I can do is I can look at the distance between those pairs as a treatment effect for that pair. I average all those together. Okay? Entirely different philosophy than the linear modeling approach. And there's some advantages to it. One being we don't care about the linearity assumption at all. So provided my units, control and treatment units are representative, and provided my matching is good enough, which is a big provided, okay, then I can get these treatment effect estimates without having to make any assumptions about planes being parallel. It wouldn't even matter if the distances are bigger on this side than this side. So long as I've got a representative sample from both ends, it'll average out to a correct average treatment effect. Okay, so that's kind of the background, what we're trying to do with the matching approach. So I took this new approach, and this was my dissertation project a couple years ago, and I said, can we apply this propensity score matching approach to the teacher evaluation problem? Can we take test scores and use those to better estimate how good each teacher is using this approach instead of the linear modeling approach? And my key finding out of that was that propensity score-based estimates are often different because they're estimating something different. What they're estimating is called the average treatment effect on the treated, instead of the average treatment effect. What that means is, using propensity score approach generally, what you're doing is you're taking the treated units and finding the best controls to match to those. By doing that, you're finding out what the treatment effect would be on those who actually were selected for treatment. If they happen to be different from the larger group, then you've only found out how good that treatment is for those you've actually treated, okay? In the context of teacher evaluation, it means all I'm doing is I'm saying, I've only found out how good this teacher is with this kind of student, or with the most similar students that I can match them from the population. And so kind of made the jump there to that would actually probably be more policy appropriate, is to only hold the teacher accountable for the kind of students that are actually given, as opposed to all possible students, which was what a linear model does. It generalizes, tries to average over the whole space, okay, of all possible students. So it made more sense. And so that was my dissertation project published. The policy findings from that, the implications are published in Harvard Ed Review. However, there's some risks. So this is where I come to today, is as I began to work on this, I started to try to understand better what's happening with propensity score matching. Now, propensity scores can be used for other things than matching. There's other ways to use them. I'm just focused on matching for this project. And again, and also there's other approaches to matching the propensity scores. Like the Halonovus distances, which I've also played with and done some innovating with, but I won't have time to talk about that. But there's some risks, and that's what I'm looking at as this project. What are the risks, and where can I find some little places to help? Here's some risks that everyone knows about. If you're missing some of the important covariates that should have been in the model, you're going to have a problem. You're going to have bias estimates if they're important, okay? But that's the same with a linear model. Not any difference there. In both cases, missing covariates is a problem. What do you do about that? Well, you have to make, you have to limit your conclusions. There's a lot of things you can do. Sometimes you just have bias estimates, and you can't fix it. That is a problem. Another thing that comes up often with matching estimates is if the treated and control groups are too different, there isn't any way you can match. And again, that's a huge problem, okay? For example, let's suppose that my treated group are 98% female and the untreated are 98% male. I'm never going to find perfect matches across those groups, okay? So that's a problem. There's some things people have done to resolve that. One is to just what they call reduce the region of common score or inference. In other words, I just make inferences about the places it overlaps. That's all I can do, is I reduce who I care about, who I'm interested in, to the place it overlaps. That's it. That's what I make my inferences about. Another thing, there's some techniques people have tried to use somewhat successfully when they do overlap, but maybe there's only a couple controls that are really high on one variable and lots of treated, okay? There's some techniques people have played with to try to deal with that sparseness at one end, okay? And then, of course, one thing you could do is increase your potential control. If you have a lot more controls to choose from, it's going to be easier. You're more likely to get some that you need. And that's a place where I feel like there's been some research, but probably not enough. So that's a place that needs some work to know that. My first workshop where I learned about propensity score matching, I was told that if you had 3 or 4 potential controls to be treated, then it was great. Well, maybe. You know, in some circumstances, maybe. In some, 2 is enough. And in some cases, 10,000 is not enough. Because the groups are, your treated units are too different, and you just need enormous potential control pool. And I actually found that with the teacher evaluation problem. There were some classes of teachers who were so unique that even with 10,000 possible matches, it was hard. It was hard to get really good matches. So there needs to be some work done there on sample size ratios. And then here's another area, the matching precision. How do you get the closest possible matches? Okay, and there's a lot of art to that. There's a lot of approaches. There's different ways in choosing how to match up the treated to the control. There's different theories about ratios, like for every treated, you should, how many controls? Because you just have one? You do 1-to-1? Or do you, for each treated unit, do you pick maybe 2 controls or 5 controls? 1,000? You know, what is it that you do? So there's a lot of work done on that and a lot of approaches, okay? I'm going to focus on this last area, which is the matching precision, okay? Most of the work that I see out there is focused on the length of that orange arrow, how far apart are those. Now that may not be measured the way you think of measuring with a ruler, it might be using some other methodology. And it's analogous, but a little different with propensity scores. But the idea is, how long is that? If those arrows are too long, then my matching is poor, and what it means is my treated and control groups might not be the same. Where I'm focusing beyond that is that I ask myself the question, what if also the direction of the arrows matters? That's a place where there's not explicit work being done, maybe some things implied in work being done to some degree, okay? And so I wanted to work on that problem a little bit more explicitly. What if all those arrows point the same direction, okay? Looking at it a little bit close. Let's suppose that we have the treatment is participation, some intervention, whatever. Outcome is, say, a math test score. Okay, teach math, so they like that. And here, let's say 2 covariates. We're looking at parental education and the student's health. Those both maybe have impact on their final test score. Which do you think maybe more?
Ooh, that's tough.
Ooh, it depends on it might depend on the age. It might depend on how bad the health. Okay.
Yeah, how bad the health is.
All right. I'm going to pretend here that dark green are the control units, and the light green are the treated, and the light green are the controls, okay? And I'm going to assume here in this case, there's these greens, dark greens you can see are shifted, they're higher, so they tend to be higher in health, okay? Just so happens in the way, you know, the kids with better health chose to do the intervention, okay? It's also shifted this way. Those with better parental education happen to choose to do the intervention. So I've got bias if I just look at the mean outcome of both these 2 groups, right? There's a little more shifting actually to the right than vertically in this particular case. Now, what we would do typically is we would say, see these guys, they only kind of matches, or these guys here, we're going to have to reduce what we call our region of common support, or the overlap, to just where they overlap. I'm not going to talk about that right now, and this is a little exaggerated. I'm exaggerating to make a point, you know, to illustrate something that hopefully, if things were this separated, you'd have, well, it just happened, not separated or worse, actually. Okay, what if the matching happens in one way more than the other? What we're going to look at is all the dark green units, because they're this way, are more likely to be matched to a light green that way, aren't they? And there's just more of them over there. The center of density of the light green distribution is not in the same place. So probabilistically, if I have a control unit here, it'll always have slightly higher probability, maybe slight, have a slightly higher probability of always being matched to one to that side. What that means, even if I pull out all these matched pairs, the dark green units may have slightly higher parental education and slightly higher students' health than the light green. And that's because the methodology is looking at simply the distance between the 2 points, but not their direction. Okay? There's nothing in an approach that I've come across or used that allows us to say, well, most of them are matching this direction, so let's try to counteract and get some on the match the opposite direction. So that's a place where I'm kind of intrigued. And then there's this further issue of what if this mismatch, say, happens mostly that direction, it happens with respect to a variable that's like really important to outcomes. What if parental education has a huge impact on student test scores? And I'm always matching smaller to the left. Okay, my arrows always point to the left. And I've got real risk of bias there.
So is that what happens nowadays? They just take the closest one even though it flows the same direction? that how
Yeah,
people
usually,
are-
it depends on the kind of matching. One of the most popular kind of matching is called optimal matching. And this optimal matching, what it essentially does is it tries to make pairs such that the sum of all of the absolute values of the distances are a minimum. And because it's the sum of the absolute values of the distances, direction is ignored. And how would you get around that? You know, do you look at, instead of the sum of the absolute values, just the sum of the distances? Well, not necessarily, because I could be because the distance is quite big, but cancel each other out. That's not good either. I mean, we want kind of both. To minimize two things simultaneously, how do you minimize two things simultaneously? It may be that you can by coincidence, but generally you can't minimize two things simultaneously. Okay, so there's a little bit of problem there that I've been stewing over. That's just a summary of that. Sometimes it'll always favor the direction towards the center of the control unit distribution. So in order to talk about some ideas I'm playing with, I wanted to show you a little bit more about what a propensity scores are. Okay, so we can talk a little bit more about what it means. Essentially, if P is an estimated propensity score, this is two covariates. What we're doing is we're saying the natural log of P over 1 minus P over the logit equals some equation that I fit. So these are my parameter estimates. Over here is the equivalent of y hat in a linear regression. Okay, it's just something a little uglier. It's just a number. You just, instead of one number, you take the log of P over 1 minus P. Okay, so every pair of points, every x1, x2 pair will have an estimated P that goes with it, but the B0, B1, B1, 2 are going to be common to all points. Just like in a linear regression, you fit those and it's the same for everybody. Okay, so then we're going to look at that. If you look at that equation right there, keeping in mind this is just a number over here, you graph it, it's a line, right? It's just a line. Make sense? Okay. If you imagine that's x and y, you have 5 equals 2 plus something x plus something y. That's just a graph. That's just an equation of a line. So for every pair of points, you have this equation that's essentially a line. So in order to just visually understand it a little better, so let's put it in y equals mx plus b form because we all like that. It's a little easier to visualize what's happening. This ugly stuff is an intercept. It's just a function of the propensity score and the other parameters. And basically the ratio of these two parameters is the slope of the line. Okay? It's just a tool to be helpful. Because then I can look at it like this. If I have, these are my treated units, my control units in light green, my two covariates, okay? Every single point pair will have the same parameters fit through, B1 and B2, meaning they'll have the same slope. So through every single point, you can imagine that there's a line. And they're parallel because they all have the same slope, okay? The intercept of the line up here is this, so it's just a function of the propensity score. What it means is bigger propensity score, the intercept will be higher. And so what I'm trying to really do, and I'm looking at this way, is I'm trying to really say this dark green one right here has that dark green line through it, that's a treated unit. To find the control unit that matches the closest, I'm not taking the unit that's the closest, I'm taking the unit whose line through it is the closest to this line. Okay, so I'm looking at the distance between two lines instead of the distance between 2 points. And that's what propensity score-based matching does that's different than like a Mahalanobis distance or Euclidean distance where you're looking at distance between the two. So, I think I've had an illustration close here. I'll be one in a minute. Yes?
Is this just another way of defining the planes?
This is actually not the same, the planes at all. Those planes had to do with fitting treatment effects, okay? So this is, we're not even thinking about the outcome yet. So those planes were like with respect to the outcomes, the difference between outcomes for treating controls. Here we've like not even thought about the outcomes yet. We're just looking at, if we go back,
How's the
going in the
angle
wrong
of
direction.
the
What?
lines that come down through each of the tree values? Yeah.
Okay, we'll just stay right here. What, I'm sorry?
How does the angle of that line get determined?
Ah, very good. The angle of that of the slope, okay, it's basically this right here. It's the ratio of these two coefficients. So if this one, the second x, this x2, has a higher number in front of it, higher estimate in front of it, with respect to b1, okay, well actually b1 is higher than b2, the slope will be steep. Okay, right? So if these lines were vertical, it would mean I had two masses of points that were like this, side to side. It would be that would be the limit. If they were horizontal, I had two masses this way. Okay? In other words, only one variable of the two mattered. Here I have a ratio of the two. Okay? So for me, this was just a visual to help me understand what's going on here with propensity scores. And what we're really trying to do, again, is we're trying to find the lines that are the closest instead of the points that are the closest. It could be that the line, well, we'll need a close-up, but the point, like right here, this one, can you see this light green is really right on that dark green line? So its two lines will be on top of each other. This point and this point are not the closest two points. This one will be closer matched to that one, or to that one, or that one, but instead it's matched to this one way up here. What it means is even though it's quite different from this one with respect to the covariates, it happens to have equal probability assigned to treatment. That's where it comes from. But then Donald Rubin and they did a rigorous proof that basically showed if you did get everything, each pair on the same line like that, okay, you're going to get covariate balance across the two covariates. Okay, even though the individual pairs may not have exact same covariates. Okay, but overall the two sets you end up with as sets have the same distribution of the two covariates if your matching is perfect. And if you have an absolutely, and this is true propensity score instead of estimated, here you have an estimated. So that's a little bit of an issue too. Although in my stuff I haven't found that to be as big a problem as the fact that when things don't match, they often don't match in the same direction, that's kind of what I found to be an issue, okay? So again, if we just look at these real briefly, if I take one point, like this one has the blue line through it, the probability is is much higher that it's gonna find a line that's close to this line to the left instead of the right. It's much higher because there's so many more points over here than over here, right? And this is a little bit exaggerated for the sake of illustration maybe, but maybe not. Another way to think of it is instead of just being these points through them all, I want the one that has, if you take the middle of the point, the shortest distance perpendicular to that line. That's really kind of what's happening as well, okay? The shortest perpendicular distance there. So, looking up close. If I were to put lines parallel to this one, this is my treated unit, through these potential controls. These are close. This one's closer, right? A little bit closer. The line, not vertical line, but the parallel, line parallel to that, through that one is a little closer than the one through here. Is illustration of what may happen. It may happen that that's the one chosen, okay? The problem is most often, again, the point chosen as a control, maybe slightly more often, maybe a teeny bit more often, will be the left rather than the right. So maybe it would have been better to choose that one just to balance things out. Okay? Possibility. So this is the problem, and I did a lot of simulation to show does it really happen? Yeah, it really happens, actually. It really happens. And if matching is not perfect, then your propensity score estimates tend to be a little bit biased. They tend to be. And more so when this line isn't quite as 45-degree angles, okay? More so when there's fewer to controls to choose from, more so when one of the variables has a high impact on outcomes, or one or more of the variables, a lot of conditions, okay? Does actually seem to happen. Okay, so here's a possible solution. One possible solution is to come up with a matching methodology that makes you choose from the right of the line as often from the left. Now again, this line is the intercept of it tells me the propensity score, or is a function of the propensity score. Okay, so basically what I'm saying is most of the time the match will be to the lower propensity score, slightly lower instead of slightly higher. You want to balance that out. Well, there's a lot of things we could do. There's a lot of things we can invent. But I just played with, for now, one idea, just to see if it isn't possible to correct this bias at all. And what I did was say, well, what if we simply exaggerate the differences to the left of the line? I make these distances bigger. I'm going to force it slightly. I'm going to force it more often to match to this side, right? Assume they don't match perfectly. It's going to force it to happen because these distances all look bigger. Well, you get into a big question of how much, That's the big issue is, well, how much? And really, where am I going here? In theory, you would make some kind of weights that are proportional to the differential probability of choosing a point to this side versus this side, given how far away. In other words, if I have 2 points equal side of the line, what's the, which one of those is, okay, where am I going to say this better? Where is it higher what's the actual probability of a point this far away being on this side versus this side? If you can weigh based on that, then it may not be major weights, it may be small weights, should balance things out a little bit. Turns out you have to have multivariate normalist assumptions of both distributions or some other multivariate distribution that you can get probabilities from. Seems to be challenging to calculate or approximate. So far, I haven't found an easy way to do that. Okay? Is there a simpler solution? Something easier guidelines we can use? Or does it even matter at all? Is this bias so small we don't even care? Okay? So my current focus is just really on playing with, are there weights at all that make a difference? Does the whole idea of even weighting at all help? And then the next step will be to look at how do you do it in a more sophisticated way so that that's more precise than what I've been doing. Okay? Another thing I want to bring up really briefly is if you look instead at if you focus on the aspect of some of these variables have more impact on outcomes than others, right? Let's suppose that the variable is, parental income has a big impact on test scores. Maybe the other one is something like the student's BMI, Actually, when I did my dissertation research, that is one that held for quite a long ways as actually having some relationship or predictive power on incomes, on outcomes, on test scores. But maybe not very much, right? Probably one's bigger than the other. Can you do something so that when you estimate it, the propensity score estimates for the fit of this line doesn't even take into account, generally, the outcome. It doesn't take into account the fact that I really care a lot more about parental education being balanced between my two groups than I care about students' BMI being balanced between the two groups. It's a lot more important. What can you do to affect that? Well, there's a lot of things you can do. One is simply shift your line artificially. Okay. Then again, what I'm doing here is I basically, when I shift the slope of the line, I artificially made one of the variables higher weight than the other. Doing that, how much do you do it? That's another question. Well, I've done some initial simulations that show if you use some basic information you get out of maybe a linear regression, it might help you to play with that. And you don't want to do it much. But if you do a tiny bit, it actually can reduce your bias because you force it to create better balance on the variable you care about when you're done. Okay? Ideally, you get perfect balance on both. But you force it a little heavy to be a little heavier on the one. So that's something else I played with initially. I just want to mention because it's kind of related here. My project, basically, my mega project I'm working on here looks at really, first of all, is there bias on propensity score-based matching methodologies and the treatment effect based on those. due to the direction of the matching, or the fact that maybe the matching precision isn't as good in the direction we care about, bigger impact on outcomes. Done enough work to be convinced those are true. Is it possible any group reduce that bias? And just show here and talk a little more detail about simulations that look really only at this matching direction, waiting to see what happens. So if I go back here, got some simulation run on this, okay? Shifted things to the left of the line just a little bit, or various amounts. I've tried various amounts just to see, is the weighting direction even something feasible if we found a more precise way to do it. So, simulation study again here. Basically, I've done 1,000 repetitions of the design. I repeated the whole process 1,000 times. In each case, I really relied on the Nyman-Rubin counterfactual framework, which, how many of you heard that? I know doctor studies. The Nyman-Rubin counterfactual framework.
Measurement people have a
measurement
whole
people.
other language.
So I'm relying on this philosophy that any person.
Experimental research design.
Yes,
We kid Richard about this.
keep teasing about it.
We actually
Okay.
understand on this already.
So just briefly, in case you don't understand. In theory, each unit has an outcome under treatment and under non-treatment. Theory. In practice, it only had one of those outcomes usually. Okay. And so instead of being able to look at the outcome both ways, you only got one or the other. Okay. So we're looking at that possibility here. First, I'm starting with a population, a pretend population of 100,000 units. And they're going to be generated under both treated and untreated states. Now, in real life, that wouldn't happen. I'm going to screen out one or the other for each unit in a minute here. For those 100,000 units, first thing, generated some covariates, either 5 or 20 in this design. Done both with 5 and with 20 covariates. Generates multivariate normal 0, 1, all correlated at that point 2. Okay. Oops. And then I've treated the untreated outcome. Is generated as a linear function of the covariates plus some random error. So basically I've said these covariates, either 5 or 20, somehow, okay, use some, is it a linear function of those creates the untreated outcome, and then plus I add in random error for each person, so each person's slightly different, okay? And then I have a treated outcome generated as that untreated outcome plus a random treatment effect distributed as just normal 1 with a small variance. So in other words, I know the true treatment effect is 1. I generated it that way. Every single unit in this population has a treatment effect at 1 with adjusted, random, centered at 1. The average of those is 1 because I've allowed some error there. Essentially, I'm assuming the truth is a linear model, okay? Which may not be true. Okay, but it's a starting point here. So in this case, the treatment effect size is independent of the covariates, which means I talked about that this was something that came out of my dissertation, the ATE versus ATP. They're the same thing here because the treatment effect size, it doesn't matter what the covariates are, it's about the same for everybody. And then I generated the probability of treatment for each of these 100,000 based on a log linear function of the covariates. Again, I took the covariates and basically said how likely you are to be treated versus non-treatment has to do with the covariates. So maybe somebody with more of X2 is more likely to end up in treatment. And essentially creating treated and untreated groups that are imbalanced with respect to the covariates. Okay. And then, sorry, I can't see from there. Basically, if I have small weights in this log linear function, then there'll be little imbalance with respect to that covariate. So if the X1 covariate is parental education, and the coefficient I put in when I generate is really tiny, though the parental education will be pretty much the same, whether you're treated or untreated, okay? It won't affect your probability of treatment. If it's big, the opposite will be the case. So it allows me to kind of look at low and high separation situations. And then I took that probability of being assigned to treatment, decided whether the person really was treated, the unit was treated, using Bernoulli distribution, which is just a single trial when you have a probability of success that somebody can generate in software. So now I have basically these 100,000. Some of them are treated and some are not. And depending on the design, it may not be 50-50, but some are treated and some are not. And then I took a sample of 100 treated units out of the ones chosen to be treated, and either 500, 2,000, or 20,000 untreated units out of the ones that were chosen to be untreated. So I'm going to be trying to match these 100 treated within either a pool of 500, 2,000, or 20,000. So this is a kind of a design factor to look at some different stuff. Okay. Whoops. There I matched, once I had my units, say I had 500 treated and 2,000 untreated, then I used typical matching protocols, optimal matching really, to match one control to each treated. I haven't experimented with like matching 2 controls each treated or something like that. At this point, only done 1-to-1. Okay. Although most of my stuff I've played with shows me it's better to have match fewer controls, because the more controls you match to each treated, the worse your matching is, and it ends up not being worth it most of the time. But in my experience, okay. And then I found a treatment effect in each of these cases, and from that, whoops. I know the true treatment effect up here because I generated it as being an average of 1. Regardless of your covariates, regardless of your traits, you're going to have an average treatment effect of 1. And so from that I'm able to figure out the actual bias in the treatment effect we found. And let's go here. The outcomes I looked at were the bias. Okay. AT and ATT are the same, so I won't get into distinction there, and the mean squared error. Just looking at the first column here, I want to show you what we did. Basically, my design was this. I had either 5 covariates or 20, and I put the 5, I've labeled it green because my theory was if you had fewer covariates to get balance on, it'd be easier to get the balance, right? Maybe, makes sense. If you had 20, it might be harder, okay? You've got more places to go wrong. Low separation versus high separation, what this basically means, low separation means that the treated control groups were generated to be very similar to each other, okay, with similar covariates. High separation, they're quite different from each other with respect to covariance. And I did it just in a flat way, either they're with respect to all covariates it's quite tight, or with respect to all covariates it's more distinguished, okay. And then I looked at, this is where I had 500 controls, potential controls, 2,000 or 20,000. And my theory was that if I had, the easiest to get good matches if I had a lot more. Okay, so I should have less bias. Well, the 0 times calling means I didn't do any weighting. This is just like you always do with propensity score matching. You just take the propensity scores you get, you find the ones that are closest using some procedure. And right here is my the bias with these 1,000 iterations, the mean bias that I ended up with. The stars mean statistically significant at 0.05. So right here, if I have 5 covariates in the model, 200 potential controls to be chosen from, and I end up with, again, the true treatment effect is 1 unit, so about 2% off in my estimate. But here you see I'm way off, 66% off. Well, what's happening over here is I've got 2 groups that are really different, okay, high separation, but I've only got 5 potential controls for each treated, a lot of balance, a lot of things that we hope are balanced in the end, okay? So this represents largely the fact there just aren't any good controls next to a lot of the treated units. They're just not there. It doesn't matter what you do if they're not there. You can't match them, so you end up with a lot of bias in your estimates, okay?
So Kimberly, question.
Uh-huh.
I'm sorry, you didn't tell us whether we could ask questions.
You may ask questions. You're good to
No, you
ask
may not.
questions.
So that situation with the 66% would be analogous to a teacher who taught a very small class.
Well, it would be analogous to a teacher whose class was very different from other classes. That in a situation in which there weren't a lot of potential controls out there in the system to even compare with. So maybe we're only trying to find similar students within the same school or the same district or something like that. There's not even a lot of potential students to look at, and this teacher's students are really unique. So that's with respect to it. It'd be really hard to find good enough matches. You end up with huge amounts of bias. Even your estimate could be way off. And you know, some of these, you know, you look at it and, well, is that really much? Well, it depends, right? I mean, in some cases, having your estimate 2% off is nothing. Maybe it's statistically significant either way, you don't care. One of the problems with teacher effects is that we often rank them, okay? Highest teacher to lowest, the lowest, you know, third of the teacher in this category, next third here, 20%, or we put them in different groups. And so to be a little bit off, you actually can make a difference to which group that teacher ends up being classified in.
That same teacher would be at the top, up above the .0090. But now
Where?
there's only 5 covariants.
This one right here?
Yeah.
Right here, yeah, I still only have 5. The difference here is I only have 5 covariates that are theorized to impact both the treatment assignment and outcomes. Only 5 that are even theorized, not 5 that I've chosen out of 20 that really exist. So in both cases here, I'm assuming I even have all the covariates there are that matter. Only 5 even matter here, and I've got them all. 20 matter here, but I've got them all. It's still going to be more likely that I'm going to be off in my balance in the 2 groups when I've got 20 than 5. Doesn't it seem like?
Much more.
It seems like it, okay? It seems like it. All right, so this is basically what happens with propensity score matching just as is. Now, if I were to find the bias using a value-added model here, I get 0. The reason I get 0 is because I generated the data using a value-added model, essentially. Generated the data assuming a linear model. So this output right here is assuming that real truth fits a linear model. That's how I generated the data in this case. I mean, I could play with a lot of other different things.
But in reality, you question the appropriateness of that model.
In the reality, I question the appropriateness. So this might be even the most simple, ideal case in which things, treatment effect is same for every student. That's one thing that's a big simplification I've even done here. Every student has the same size treatment effect on average. It's independent of their covariates. Doesn't matter what trait they have, same treatment effect. And linearity exists. So this is even a simplified case. We end up with quite a bit of bias in some scenarios here. Okay. So that's kind of the concern. Now, from here, let me uncover. This is with weighting. Basically, I played with, after some experimentation, weighting those to that left of that line, 2 times 5 times 10 times, okay? And what I've got here in bold is basically the minimum in that set here, okay? So if we look at this one right here, that is the bias, just standard propensity score matching. This is where the bias ends up using a 2 times weight of those to the left. In other words, trying hard to pull more of the matched units to the right of the line. And then it gets worse, okay? Which means I've overshot it and I've pushed the bias really the other direction. Here I've overshot it. So getting the right weighting is something that's going to require more sophistication than just playing with 2 times. Now I'm going to have to look at probabilities of distributions and so forth. Yes?
So, Kim, I don't see any pattern in that. Is there?
Yeah, you have to examine closely to start seeing the pattern. Let me talk through the pattern here a little bit, some of the things I see. First, let me just show you a couple things, and then we'll talk through that. One is there. The margin of error here is around 0.015 It varies from spot to spot, but it's all like 0.04 to 0.014 to 0.017. It's all about 0.015 is a good rule of thumb. So you can see here, this was a statistically significant fix in this case. Other cases, it's made it worse. This is where the problem is getting a case where it's consistent. I'll talk about the patterns in a minute. I just want to show this. This comes up a lot of places where it was better adding more weight, but now it made the bias worse. Okay, which makes sense. You don't want to you overdo it. You're going to overdo the bias. Down here, I think I mentioned this is just there. A lot of the bias is from another source, which is just there aren't matches. Groups are too different. There's not enough controls. And over there, it ends up about the same, but I've pushed it the opposite direction. Now, the patterns that are fine here, you have to, examining it here, what I'm finding is you want to look at where the bold numbers are. Now, these aren't statistically significant. If I wanted to see a little bit more what's happening here, I need to do more than 1,000 runs. Maybe I do 10,000 runs, and I may get more clarity up here. But basically what I'm seeing, and it's not perfect, is that if you look at the reds, okay, where I theorize the matching will be a little bit harder, typically when matching is harder, more weighting tends to be the ideal solution. Okay, where here you can see that matching is a little bit harder, again, with high separation, more covariates and so forth. I need a little bit more. Down here, because I've got 200 potential controls, I didn't need quite as much. So examining it kind of closely, I'd like to repeat this again with more runs, so I have smaller standard error. But generally what I'm finding here is the harder it would be to find matches to begin with, the more weighting is helpful. In other words, when my populations are really quite similar to each other, you're not going to have as much bias in terms of probability being to one side of the line versus the other, because they're quite similar to each other. The more different the populations are from each other, the more that becomes a problem. And it needs a little bit more. I need to run it with again with maybe 10,000 and pull my standard errors down to see it a little bit more clearly. There's only one case right here where the lowest bias is with no weighting. That's one thing I find. This is the easiest possible matching case in the whole situation. I've got green, green, green. In other words, not very many covariates really exist. A lot of potential controls. The two populations start out real similar anyway. In that case, the weighting doesn't help. At least with these levels, it may be a 1.2 or 1.5 instead of 2 times would have helped. Okay, and over here, so it's hard to make too much judgments when they're not statistically significant. I'll look down here a little easier to see. Okay, this is the hardest among these options. Okay, this one is quite a challenging to match situation. I don't have a lot of potential controls. A lot of weighting was helpful. With more controls, as in these two cases, a little bit less weighting seemed to be ideal. So one factor that seems to be a recurring pattern is how high part it is to match to start with. Now again, that probably all has to do with the distributions of the two sets, the control and the treated units, and there may be some things more sophisticated that can be done with those functions to understand it. This is that MSE, the standard error. It's the same pattern, so I'll go through that. Basically, my finding is there does seem to be some directional bias. Whether it's practically significant or not, or even statistically significant, that's going to depend on the study and what you're doing with it. It is possible to overshoot and make the problem worse, or to reverse the direction of the bias. When matching is harder, then a larger weight seems optimal. It's easier, a smaller weight seems optimal. And weighting does seem to help a little bit, except in the easiest to match case. In other words, these covariates are pretty, these two distributions, the treat and control, are pretty similar to start with. So some future research here will be to look at, this is a primary one, refinement, and that may just take some you have to start making some assumptions about the distributions. Are they multivariate, normal, and finding probabilities and looking at that. I've also looked at, I mentioned very briefly earlier, shifting the angle of the line to favor the high impact covariates. And again, some pilot simulations of that are very promising that it can be helpful. Another avenue of research is to look at, instead of propensity score-based matching, Mahalanobis-based matching. And again, I find that there's some innovations I've played with there that are promising, doing some, you do some weighting of the covariance matrix, and it seems to be very helpful. Application to teacher effect estimates pilots promising, and the feasibility of data sets. So a lot of things to look at there. Just real briefly, I wanted to show you an application to some teacher effect simulations. I don't have the full detail because it's really quite complicated as how I put together in other words, how you create the truth that you're trying to see if they're seeing it, if your estimates replicate. And basically used some hierarchical models and looked at some assumption violations and assumptions of linearity, violation of linearity assumptions, and some other things, and kind of looked at what would happen. And I don't have time to go into all that. It wasn't my purpose. But I just wanted to show you briefly application back to estimating teacher effects. The model I used assumed a couple of things. Assumed that there were some missing covariates, which meant I had some errors correlated. It meant that I assumed some lack of linearity, and so forth. So I made some assumptions that would potentially make value-added estimates not so good. What this is the correlation for a set of 100 teachers of the truth, okay, with what I estimated using these various methods about the teacher's effectiveness. Naive effect means I just compared that teacher's test score mean to everybody else. Low, not a great correlation. Value added, higher, okay, but lower than the rest of these. And again, I was intentionally creating assumptions that would be a problem for value added, but that exist in the real world. Student growth percentile is a little bit better, but again, it depends on what assumption violations you throw in there. And a variety of matching-based methods tend to do better, but you know, as I fiddled with various assumptions and different parameters and so forth in the model, consistently the pattern is these guys do a little bit better than these guys. So it's promising that the propensity score approach could be very helpful. The propensity score is a traditional method. This is using distance weighted, like I just showed you, with some slight revisions to it, a little bit better in this particular case. Okay, Mahalanobis distances did even better, and this is another innovation I haven't showed you that is something I've been playing with did even better. I'm showing there's a little bit of there's some promise that within these matching approaches we might get correlated with the truth just a touch better. Yes.
So this is wonderful. How can you give us a sense of how much more difficult some of these methods are from others? You know, for example, if it's just some state department of assessment, maybe they're not completely trained as well as they could be. How important is, like, how much more difficult would be propensity score be from student growth percentiles if the effect is not that different? You know that.
Yeah, it depends on how big the effect difference really is in that situation. The problem, the greatest difference, I think, okay, all these matching ones art to them. You know, so there's many ways that you can do them. And it's not a black and white, put your numbers in the black box and they pop out, right? So that's a little bit more challenging. Having said this, you know, value added, of course, that's linear regression. Anyone knows regression theory to do it, maybe. And student growth percentile is a little harder. You have the right software, it just pops out for you. People have written packages to do it. As far as usability, I think it gets down to the software. If you had smart enough software developed, that it's using its own self-analysis to make the decisions and create the results for you. Or if you have some general guidelines as to this works more often than this, most often it works best to have this matching ratio and use this approach. And then any kind of software design would be fairly quick to use and get it right. I know, Mary, you played with the R package for student growth percentiles, right? And that's what a lot of people use, is my understanding.
Yeah, it's kind of scary, in my opinion.
It's scary in terms of how well programmed it is.
Yeah, and because there's nobody looking at it really.
Yeah,
You know, they're just assuming that's the truth.
yeah. And as far as usability,
No, it's horrible.
yeah. But
She
if you look
just
at it-
understated the case.
Yeah. But you'd have to argue that the same thing as here is true depending on, I mean, this is why, you know, that whole EVAS thing, is it still called EVAS? It's called something else now. I mean, this proprietary software to do this, it's not like you've got principals doing it on the computers, right? Because it's something that any of the methodologies require a lot of sophistication. One of the things that I like, regardless of what details you use here, is I feel like there's some simplicity into being able to say to a teacher, we compared your students to the most similar students we could find out there. And your students did a little better or they did a little worse, right? As opposed to this, okay, where, you know, a coefficient and a random effects model or, you know, a fixed effects model, it's a little bit harder to explain to a student, to a teacher, we've adjusted for all these covariates in the model as opposed to we've matched on them. So there's a little bit of conceptual simplicity in terms of interpretation, I think. I think not everybody might agree with that. This one, I think, if it's explained well enough, I think maybe, I don't know, you know. I think it's a little, the details are a little hard to get. So I think there may be some advantages to being able to say, so compared to the most similar students, your mean was 1 unit higher, 1.3 higher, as opposed to be adjusted for all these covariates in a linear model and it showed you an effect size. Right. I think it's a little bit of improvement, but I don't know. So now to answer your question, Dr. West, I think all of them are very challenging to use for Joe education and
Educational person in the state office.
Yeah.
That's the thing that's scary, because that's what we
Yeah.
need to get to is, we need to make it possible for this to actually become policy. Which is so hard. Maybe like you said, if we can build the software to do it, or I don't know.
Yeah, yeah.
Have you thought about having, I don't know, maybe you call it the Q measurement or whatever.
Q measurement of what?
But difficulty of matching, right? Because,
Q effect.
because if you could measure that and say, okay, this is what we have, what is the difficulty, give it some value that makes sense to the average human, the difficulty of matching this.
Yeah.
And
I
then
think-
you could possibly use that to adjust your weighting, but that alone would be able to have the average Joe say, yes, but notice what the difficulty of matching is.
Okay, maybe. One thing that became clear to me as I was working on all these simulations was there are not good guidelines as to even how many controls you've got to have to select from in order to get good enough matching, right? And that is kind of related to what you're saying. It's a place where itself, apart from all this other stuff I've been doing, needs some work is how many potential controls is optimal under X conditions. That's related to what you're saying, and that's a place where I almost feel like, I'd like to back up and do some work, because there's not enough guidelines, I think, out there to even know. I mean, I went into my dissertation thinking, I've got like a pool of 10,000 students to match to a class of 20 at most, because of the way at most I had 20, or so, maybe 22. Out of 10,000 should be no problem, right? Oh, it was a big problem sometimes. Because as a set, these 20 were very unique. And so it was much more challenging to even think. That was a big surprise to me. Other questions?
So you've got some interesting simulations studies here. I actually think they're really interesting. Are you publishing those, or do you?
I have one under review. It doesn't go into any of this about weighting or how to attack it. All it does is it looks up the amount of bias and propensity score-based estimates under certain conditions. And the conditions have to do with specific covariates. Well, actually, what I did is I have a set of covariates that are fairly ordinary, and I take one covariate that I alter and make it either much more highly predictive of treatment. So I vary that factor for that covariate, and then I vary for all the covariates how much impact they have on outcomes. And looking at what happens is your bias and your propensity score estimates increase, the more you have at least one covariate that's highly predictive of outcomes. In other words, it's separated in that dimension quite far. It's not surprising. And a lot of that is really because there aren't matches available. But of course that exaggerates the more that dimension where there's separation has a high impact on the outcome variable. I'm not getting good matching in this direction. And so I've got one that's just a series of simulations just focusing on, hey, here's a problem. And that one I should hear back from any day. Other questions?
So how practical is propensity score matching in the context of estimating teachers' value added?
What do you mean by practical?
Well, I mean more than practical. I don't mean just practical. Is it likely to solve the problem that it's proposed to solve in that context?
It's likely to make a small improvement. Philosophically, where I am at is we shouldn't do it at all. But if we are going to do it, let's do it a little bit better. That's where I'm at.
When you say should do it, you mean?
We shouldn't try to link teacher quality to student test scores at all using any statistical model there is. That is where I fundamentally fall on the spectrum. There's a whole lot of research I would like to do regarding effects on teachers of this. Effects on teachers emotionally, effects on teachers as far as retention of teachers. There's a little done there already. Effects on teachers' teaching style. There's some things we know. But one of the key things I'd like to do is a real good study, maybe a qualitative study at least initially, looking at how do teachers feel about all this? How do they think it's impacting them? What do they think we're doing wrong? We all kind of know. We all kind of know that most of the teachers are fairly negative. I would suspect that newer teachers are accepting it worse because they've not seen any different. But that's something I'd like to look at in a lot of detail.
So given the attractiveness of value-added models to policymakers, you'd be marching upstream.
Well, see, here's the problem is policymakers say we should be able to do it. How hard is this? How hard is it to look at student test scores and know how good the teacher is? Well, it turns out it's really hard. And the policymakers really think it's not. And I ran into that in my current job where someone came into kind of an administrative role and said, we just got to link everything to student outcomes, just link it all. And I just went, well, first of all, our class sizes are really small. That's an issue. Anybody who's done any stats knows that sample size is a critical thing, right? You have a teacher with how many students? Well, if they're in high school, they may have a lot, although some of them are within classes and we have correlated errors there and stuff. But a typical elementary school teacher, what's our average in Utah, like 24 or 22?
It's probably a little
About
higher.
the average graduate faculty instructor who has 6.
Yeah. Yeah. And my sister's a high school teacher, and she's just raging on the. She was having a meltdown over this the other day, and over Easter dinner. She was and she says, well, here's the thing. thing. She says my AP students, I don't have to spend 1 minute on test prep when we have the highest test scores in this, right? Well, yeah, adjusting for all these things, like value-added knowledge, using some of these other things, would it bring some, I don't think completely. And then she says, my fourth period, they are just evil. They're just out of control, coming in. And I think teachers have these perceptions a lot, that this class is so bad, there is nothing I could have done to promote even average gains in them. Well, this class is so amazing, and there was such spirit of camaraderie and all, peer effects going on in the class. And so now this class is so excited, I didn't even need to be in the room, and these students were going to have huge gains. So how much of that is truth in her mind, and how much of it is fiction? Yeah, I don't know completely, but I do know that if there's not teacher buy-in, because the teachers don't believe it's going to happen, then it's not helpful. If the teachers do not believe that by seeing numbers on the screen, to have somebody come up and say, you're a 1.2, right? Okay, now fix your teacher. Okay, do it. Fix your teaching at 1.2.
Yeah, we're talking about teacher evaluation. This is a tangent, but you were mentioning peer effects, which I believe in a lot. I wonder if we should be doing some research in terms of we study the effect that teachers have. What if we attached effects to certain students and said every time the student walks into a classroom, the whole class gets dumber? They just go down.
That's
They're
so
smarter,
that's a good point.
They just go down or they go up, and then we can attach some kind of effects to particular students.
And then we can just get rid of those.
I think it'd be hard.
kids.
I don't know.
But it might be more honest about what really happens in the classroom.
Well, yeah, it might be. I don't know offhand how you would do it, but I think yes.
Just talk a bit about the stability of the effect. Is that really a factor? I mean, I've been a teacher in high school for many years, and sometimes I was great, and sometimes not so much. And we're talking about a stable effect, right? And that really
It's
isn't
not a
just
stable
something-
effect. I mean, there's plenty of research out there indicating that it's not stable.
Does this account for that?
Well, this is simulated data, so I would have to say theorize that it was a certain amount stable or unstable and see if my estimates recovered it. As opposed to really knowing whether in the real world effects are stable. That's something we require more real data. But the data out there, the study out there suggests they're not particularly
There's the issue
stable.
of a single teacher being effective for some of the students in the class, but not others.
See, that has to do with the treatment effect size. If you think of a linear model, it assumes it's the same size treatment effect for everybody. Well, it's probably not, right? It's probably not. And so if you have a teacher who has a bigger effect maybe when they have gifted students, they're good with those kids, right? If they get more in their class this year than last year, then that's going to bias their estimate upward that year, right? And it can work the other way around too. So then there's the other. There's a lot of other issues. For example, students make a big jump one year, they tend to not the next. So there's a lot of big problems with it, and that's where I started out with this, was kind of being unhappy with what was happening value-added, because I felt like it wasn't going to be the estimates were going to be valid, not good validity estimate. Validity evidence. Some people say there's some, but then you look at it and I question it. So I don't know.
What do you propose policymakers use? They
I
can't use a
suppose-
crystal ball, so
Yeah, they
they
don't
have
have-
to use data.
You have to. Well, no, the data doesn't have to be test score data. I don't ever feel like they need to throw out looking at test scores altogether. But I think it needs to be one piece in the puzzle. In Colorado, it's 50%. That's by law. So that's too much. I don't have any problem with it being one piece, such that if every other part of the teacher's evaluation is high and this is lower, we can account for it. I also have a little bit of philosophy that probably a lot of people would disagree with. Okay, and you men would probably disagree with it, statisticians. that it might actually be better. But if you could use it, see, everything in the wrong hands is a problem. But if I were a principal in my school, the evaluated effect it's hard for me to know what that really means. What covariates did it adjust for? What did it didn't did it not, and what did it over adjust for? It'd be really hard for me to understand that. I would rather just know, frankly, the test score mean for this teacher versus this, and then I go in and place the context on it. I go in and I say, I know that teacher had a really rough class full of students.
But then you have the bias of the administrator, because the
You do,
administrator
you
might
do.
not like that
Yeah.
particular teacher, their methodology,
You
their
do have
religion.
some problems with that. So it's sort of like there's no easy solution. I mean, in an ideal world, you could bring, if you had endless money, you can bring outside impartial evaluators in, right? Incredibly expensive. So, do you throw something out because it's biased? Well, I might say that wrong information is worse than no information. Some people say, but it's the best information you got. Yeah, but if it's wrong information, that's worse than no information. That's what I think. Having said that, I don't really think this is no information. Okay, I do think that you'd get some information out of any of these estimates about a teacher. Just would hate to put too much weight on it. Yeah, was it hope or?
Kim, I came in believing that propensity score matching was a wave of the future. Now I think it's just that equal fourth period class. I'm just gonna have to go with the teacher's gut reaction to the class.
It's not a panacea for all woes. And there's plenty of problems. It's really, the biggest issue is how close can you get the matching in the
Actually,
end.
I'm comforted by the position that you take, where you're, our tools are becoming so sophisticated that that now even the people who are supposed to be using the tools to make decisions won't be able to understand what they're telling us, like principals and legislators. And as you say, we're likely putting tools in the wrong hands that are very powerful and can create all kinds of misdirection.
Well, everybody sees cases, they come up in the media all the time, you know. So-and-so was star teacher last year and this year they're on probation or whatever. You know, those kinds of things happen, and that's because of the instability of these estimates. Fundamentally, you know, teaching quality is a very multidimensional construct, I think. And so how can you ever capture it with one number?
Have you done much with Bayesian probabilities, and could we use that to kind of weight the probability that certain data provide good information and good evidence on particular learning outcomes, and maybe kind of create models that say some outcomes are better determined by certain kinds of data than other kinds of data?
Maybe. Yeah. Yeah.
You want to know about Bayesian, you ask her, she'll tell you.
Well, I understand it. I understand the basics of it in theory. I understand how to use it when a software program spits it out for me. The connection between those two, maybe, I don't quite have yet. I needed to.
I have a nice boring book I could loan
I have some boring books on it too.
I didn't get all the way
It's
through it. It
a-
sounded interesting.
It's interesting in theory, and I think it can be very useful, but I don't know about the scenario you mentioned, but I think it can be very useful in theory. I mean, in theory, I mean, if you had, what Bayesian estimate does is it updates with, you know, these prior information updates with new information. I mean, in theory, I guess you could do something with a teacher where you look at, you know, constantly updating, using that. I don't know how useful that would be really. I don't know, because you don't really want teacher quality to be a stable construct, do you? You want teachers to be improving, right? So if you don't want to be thinking of it as I'm getting a finer estimate of a stable quality. We want to be able to distinguish instability in the estimates because of contextual factors, because of different students in the classroom, the fact that the teachers are really improving. I think that we put a lot of faith in quantitative measures these days, more so all the time, and I think that a lot of times we shouldn't. A lot of times you can learn a lot more by a good observation than you can by a lot of test scores and numbers. Otherwise, I'm a quantitative mental, you know, I like it, I think it's fun. But There's a lot of cases when just use your eyeballs, you know, go look outside and see that it's raining instead of analyzing the data, you know.
Any other questions? All right, thank you, Kim.